so much for presentation. Can you hear me?
Yes, we can hear you.
And most importantly, can you see my slides?
Yes, we can.
Great. So thank you all for having me. It's great to be here. So today I'm going to talk about climate models, and in particular, how we represent land in climate models. And we will see this is very closely related to computing. It's a very... do you see? Okay. So first of all, why do we care about land? So we live on land, but usually when we think of climate models, we think of models of the atmosphere, of rainfall, clouds, and so on. And so first I'm going to argue that land is very important for us. For example, for food security, for extreme events, droughts. So we do care about predicting how much water will be there in over which time scales, for a large number of reasons. So we do care about land for our living, but also for the effects land feeds back into the climate. It has effects on the atmosphere itself. So these are the two main reasons why we do care about predicting the evolution of land. And to do so, we use climate models or land models. And the main issue here is that the events that we see on land can span very different time scales. For example, at the scale of a single event, we can think a few hours or a few days. We are interested in these kind of events, for example, for managing a hydroelectric dam or for water regulation or for extreme events. And so these are what we usually deal with using hydrological model or weather forecasting models. But then if we upscale, we can look at the seasonal, for example, at the evolution of land over a growing season, which we're interested in for agricultural purposes. And if we upscale more, we can study the evolution of land over decades or centuries. And this is what we use climate models for. So for all these applications, though, we do need to have a computer model which describes all that happens on the surface of the Earth over land. And what has been developed in the last few decades is the so-called Earth system models, which couple the atmosphere, land, and ocean. And in particular, over land, we can see we have a lot of complexity to describe because we have so many natural and anthropogenic phenomena. For example, agriculture, evolution of vegetation, snow, mountains, all these objects, all these components of the land system do interact very tightly with atmosphere, exchanging water, heat, and other quantities. And so we need to capture as much as possible of these very rich physics to predict the evolution. And so to solve the problem, the state-of-the-art models that we use are computer models which describe ocean, land, and atmosphere. So we can think of these as separate components. We have a computer model for the atmosphere, a computer model for the ocean, and one for land. And we can see that the Earth, so atmosphere and land and ocean, are discretized in grid cell. And within each grid cell, what the model do is solves the mathematical equation of the physical processes that we want to describe. For example, land will receive rainfall and other quantities from the atmosphere, and then it will compute, it will evolve. So for example, vegetation is evolving, the water storage, and a lot of other quantities which we're interested in are the object of calculations. And it gets really complex. So for example, biogeochemistry, vegetation, fires, human activities, irrigation, fertilization. So it can get really complex. But how can we describe all these phenomena, all the heterogeneity of land using this simple discretization in grid cells? Well, we can take a look over the past 20 or 30 years of these models, and we can see that the resolution has been increasing. This, for example, you can see over Europe elevation, and the properties of land can be described more and more with increasing resolution, which helps. But the bottleneck here is that if we keep increasing resolution, we are going to hit a bottleneck, which is the available computing power. And if we dive a little bit, since this is a computer science conference, I need to show this plot. So the main bottleneck is, in this case, computing. And we've seen over the last 20 years a slowdown in the increase of frequency and power used by a single processor. For example, you see the red points and the green points. The steady rise, what used to be a steady rise of CPU speed and power has been decreasing. And so what we are left with lately has been increasing the number of transistors and increasing basically the number of cores. And so these models try to adapt to the available computing power. And so this is very important to project what is going to happen to the future of this computer model and how should we develop them to take advantage of the available computer architecture. And to take a look at what happened, aside this, the history of computing, let's take a look at the history of these models, which developed over the same few decades. We can see this is the timeline for the climate models developed at GFDL here in Princeton, New Jersey. And so we can see in the 60s, the first actual global climate models were developed with the interaction of cloud and radiation. But then as computing increased, two main things happened. Resolution was more kept increasing, but also the complexity of the models. And so, for example, models were able to resolve hurricanes since the 70s, and then more and more complex things. If you look at the latest, in recent times, we are able to include in the models things like projecting fish stocks and other available fisheries, and more extreme hurricanes and storms, and more chemical compounds and more variables. So basically, we see that more computer power gives us a more rich model, so we can study more problems which are connected, for example. But also the increasing resolution it comes with this. And now we ask, can we keep going like this, or should we try to look at different solutions with the incoming change in available computing? Now, so what happened? Yes. So one possible, a very hyped argument right now, a very hot topic, is the use of machine learning to overcome, to some extent, the limitation in computing available. And so one question I want to briefly talk about is, can machine learning help us with the evolution of these models, with the development of these models? And there are some challenges here. So when I talk of machine learning, I talk about a set of statistical methods, which probably you've heard about, because these days it's very common, and we hear a lot about it from private companies using it for insurance rates or all kind of applications. So one very common techniques, for example, is neural networks, which I depict here with a simple scheme, which basically is a complex statistical model to link inputs to outputs, so to link different physical quantities. And one interesting application is the so-called convolutional neural networks. So if we can see on the right, the use of these convolutions or operational images gives us the way of treating 2D or multidimensional, basically, images. So this is a very common tool, and there's been a lot of work trying to use it to improve efficiency on climate models. Or even use these tools as emulators. So instead of developing these computationally expensive climate models, some researchers say, why don't we directly base everything on these statistical models? So I'm going to just give you two examples of why it is difficult to apply this to climate. And one of them, the first challenge, is the multi-scale nature of some of the processes which are computed in climate models. And so, for example, you can think of the clouds during a sunny day. So it's not like the problem is not like classifying cats and images of cats and dogs. One key properties of these phenomena is that they occur over a huge range of scales, from kilometers to millimeters, basically. And so when we feed to these statistical models data at one scale, it's very difficult to generalize at other scales. And here I'm just showing very recent research of like 2022 of people trying to actually generalize neural network to these multi-scale problems. So it's actually a very, very open field and very interesting, but it's still a challenge. And a second challenge of using machine learning for emulating climate problems is that if we feed data to these methods, you know, they learn from data, but they do not easily learn the laws, so the equations behind the data. And so, for example, we can teach these models to emulate the evolution of the climate, but some basic laws, for example, the conservation of physical quantities such as water or heat, it's very difficult to have a model but fitting the data very well and observing these physical constraints. And so this is also actually a very hot topic, and there is a lot of, many people are working on this, and this is another recent paper which you can check out. But the interest is there, and for example, even companies like NVIDIA are building computers with the objective of emulating climate problems. And so it's very, there is a lot of effort right now, despite these challenges, to use these tools, because the data, there's so much data that it's like worth a try. But in the context of land models, I'm going to show you how we can use now some machine learning techniques to optimize the existing models. And I've shown you the importance of land, of modeling land, for example, the availability of water, heat, and so on for our livelihoods. Something where machine learning can help is model the heterogeneity of land, which is very, describing it with a traditional computer model is very computationally intensive. Because within a single model grid cell, we can have a lot of like different crops, natural areas, and so urban areas. And so can you capture all these features using machine learning and then improve model performances? So what have been done in the last few years is actually, given a grid cell, we collect a lot of information about it. For example, the map of elevation and a lot of other environmental data. For example, slopes, temperatures, precipitation, and so on. And based on all this data, we partition land in a little units which are very homogeneous in itself. So for example, all pieces of land with the same elevation, with the same average precipitation, and so on. And once we do this partitioning, we put them back together using a clustering technique. And so we get a very high resolution map of land reconstructed and clustered together in a few clusters. So why is this useful? This is actually very powerful because we can take a traditional grid cell of a climate model. And if we do this clustering, we can actually solve all the physics happening within the grid cell for each cluster, and then map the results in space. And so, for example, here I'm just showing an example of simulation in which we study evaporation. And we can see that doing this clustering, we can use a traditional climate model and actually map the results back in space. And for example, you can see that even something like the river network here in blue in the picture is actually very easily, you can see basically the river, so the area where you have a lot of evaporation. And so this is an example of how using a clustering technique combined with a traditional computer model of climate over land can give us a very, very remarkable results. So we can more efficiently describe very heterogeneous surfaces. And so a second example of this is solar radiation over mountains, which is an interesting problem for climate, but also if you think about it, it can have other applications, for example, agriculture or the yield of solar panels over a very three-dimensional terrain, like with not a flat surface. And so even in this case, the physics is quite complex because we have solar incoming radiation over a 3D over mountains, so we can have reflections, shading, all sort of processes. But using this kind of approach, so taking land, clustering in a few, using a machine learning clustering approach, we can come up with a few clusters. And then for each of them, we do the calculations. And I'll show you an example of results. So we can see in these maps that we can, what is the true physics, which would be a very high resolution field. We can approximate it with just a few tens of tiles. So a few tens of clusters. And the importance of this is that what would be like, to do the full calculation, it would be like around 1 million data points, let's say. And using 10 or 100 clusters, we can already recover like 80% of the original map. So clustering in this case is very powerful because it gives us a huge boost in describing very spatially varying problems using just a few data points. So I'll leave you with this. I'll just summarize that describing land is very difficult because the processes involve so many scales and they are so variable in space. So machine learning can actually help us improve the existing models that we use. And I'll leave you with this. And if you're interested in this or more details about how climate model works, feel free to contact me. This is my email. I'm really interested in chatting about this. And welcome any question either now or after, I don't know, at the end of the hour, whatever works best.